Hello, everyone. I'm Lei Tao from Nankai University. I will present our work giving every modality a voice in microservice failure diagnosis via multimodal adaptive optimization to you. This is a collaborative work done by researchers from Nankai University, Microsoft, National University of Defense Technology, and Tsinghua University. Let me first introduce the background of this paper. The microservice architecture has been widely adopted across various industries. The microservice architecture decomposes applications into independently deployable services, each handling specific business functions, offering high flexibility and maintainability. A microservice system may consist of thousands of individual microservices. However, microservice systems' complexity and dynamism pose reliability and availability challenges. Failures in one service can propagate across the interdependent services, significantly impacting user experience and causing substantial losses if not promptly diagnosed and remedied. Rapidly diagnosing the type of failure in a microservice system helps operators trace and implement appropriate remedies. Collected metrics, logs, and traces in microservice systems can be utilized to detect and diagnose failures. Metrics are time series data reflecting business status and machine performance. Logs are unstructured text outputs from program executions, and traces connect service invocation information into a tree-like structure during a business call. To simplify data processing and capture complementary information among different modalities, existing multimodal failure diagnosis methods have mapped multimodal data into a unified representation space. However, they overlook intermodality differences and disrupt the structure of information stored within each modality. Therefore, how to analyze multimodal data, leveraging information from various observation types, is a challenge. Mainstream microservice failure diagnosis methods, such as GAT-based EDRO, event pattern-based NESA, event graph-based GRUT and diagfusion, couple various modalities together when extracting and fusing multimodal features, relying on multiple modalities simultaneously. These methods often assume a scenario with complete and high-quality multimodal data, which is not always feasible, leading to potential performance degradation when the data is incomplete or of low quality. Previous multimodal failure diagnosis approaches have mostly been based on deep learning. Training a multimodal data-based failure diagnosis model with unified learning objectives using the same training strategy may not be globally optimal due to different training convergence rates across modalities. During training, high-yield modalities with better performance tend to suppress the optimization of other modalities. As a result, low-yield modalities cannot fully utilize their features due to interference from other modalities. Therefore, how to reduce the negative impact caused by inconsistent convergence rates and mutual interference between different modalities is a challenge. In summary, for the task of failure classification in microservice systems, we have identified three main challenges: inconsistent data formats, incomplete and low-quality data, and interference in modality optimization. To address these challenges, we propose Medicine, a modal-independent microservice failure diagnosis framework based on multimodal adaptive optimization. This is the framework of Medicine. Medicine consists of three stages. The first one is feature encoding. Each modality of data is encoded separately. Second, modality fusion. Encoded features are fused, retaining initial features for comprehensive representation. Third, optimization balancing. An adaptive optimization module adjusts convergence speeds across modalities to enhance overall performance. In the feature encoding stage, we design specific data processing, feature encoding, and classifiers tailored to the granular knowledge stored in metrics, logs, and traces, reflecting different failure types. Consider a system where metric anomalies indicate CPU spikes, logs detail error messages, and traces show delayed service interactions. By designing information statistics paradigms and encoding each data type separately, we preserve their unique information, enabling precise failure diagnosis. In the modality fusion stage, we employ a multimodal fusion module with channel attention to integrate the original statistical features from each modality with the failure classification features extracted by the feature encoders. This module is designed to effectively combine information from different modalities, ensuring that the unique characteristics of each modality are preserved and enhanced. The fusion module performs the following steps. Feature concatenation. Concatenate the features of different modalities and use a fully connected layer to generate an integrated feature representation. Modality-specific linear transformations. Each modality's features are separately processed through individual linear layers. Channel attention mechanism. The outputs of linear transformations are passed through a sigmoid activation function to produce attention weights. Feature stacking and squeezing. The original and attention-weighted modality features are stacked and processed through adaptive average pooling to reduce dimensionality and focus on key features. Classification. The pooled feature representation is passed through a fully connected layer to perform failure classification. In the optimization balancing stage, the multimodal adaptive optimization module is designed to address the challenges of inconsistent convergence rates and mutual interference among different modalities in multimodal failure diagnosis. This module comprises three key components: modality evaluation, gradient suppression, and feature enhancement. These components work together to dynamically adjust the training process, ensuring that each modality contributes effectively to the overall model performance. Modality evaluation is the initial step in the adaptive optimization process. It assesses the contribution of each modality to the learning objective by calculating the ratio of validation loss reduction to training loss reduction. This ratio ρk indicates the generalization performance of modality K. The contributions of all modalities are then normalized to ensure their coefficients theta k sum equals 1. The gradient suppression component dynamically adjusts the learning rates of different modalities based on their evaluated contributions. For the dominant modality, the one with the highest theta k, the gradient is suppressed to prevent it from overwhelming other modalities. Here, alpha is a hyperparameter controlling the degree of suppression, and S represents the suppression factor for the gradients. This approach ensures that the dominant modality does not excessively influence the training process, allowing underperforming modalities to catch up. The network parameters are updated as Formula 4. In this formula, omega t is the current parameter value at iteration t, and omega t plus 1 is the updated parameter value for the next iteration. The term eta represents the learning rate, which controls the step size of the update. Finally, g is the gradient of the loss function with respect to the parameter omega t, guiding the update direction. This update rule ensures that high-performing modalities do not dominate the optimization process, allowing for more effective and balanced training across all modalities. To compensate for the lower contribution of underperforming modalities, the feature enhancement component boosts the features of these modalities. The scaling factor for the weakest modality, determined by the lowest evaluation score, is calculated as Formula 5. The enhanced feature representation is given by Formula 6. In this formula, X represents the enhanced feature vector for modality K. The term U is the original feature vector of the modality. The function f scales the feature vector u by the factor s, effectively enhancing the features of low-performing. We evaluated medicine's performance on 3 widely used public datasets collected from benchmark microservice systems. The experimental results demonstrate that medicine achieves comparable or superior failure classification performance compared to state-of-the-art single-modal or multimodal failure diagnosis approaches. Specifically, medicine improves F1 score by 41.49% to 93.90% compared to single-modal approaches and by 15.72% to 70.84% compared to other multimodal approaches. We simulate the online detection environment to analyze the complexity of medicine and other multimodal baselines by calculating the average detection time required for each failure case. Medicine demonstrates the shortest detection time on D1, taking only 3.44 millisecond, whereas Cloud RCA is the slowest at 35.16 milliseconds. On D2 and D3, medicine's average detection time is comparable to that of micro-CBR, all around 5 millisecond. Compared with baseline methods, medicine is indeed efficient in diagnosing failures. The results of the ablation study indicate that medicine significantly outperforms unimodal methods. Our designed unimodal encoder can extract useful features based on the characteristics of microservice systems for failure classification. Multimodal adaptive optimization dynamically adjusted and optimized the weights and interactions between different data modalities, thereby enhancing the overall performance of the model. In conclusion, we introduce Medicine, the first parallel microservice failure diagnosis framework that achieves modal independence through multimodal adaptive optimization, reducing reliance on individual modalities. We design specific feature encoders for different modalities of observability data based on their unique characteristics and the types of failures they reflect, enhancing the ability to comprehensively capture knowledge within each modality. Our design module, combining modal evaluation, gradient suppression, and feature enhancement, maximizes the potential of multimodal data by adapting to different learning paces. Extensive experiments prove medicine's superiority over existing multimodal failure diagnosis approaches for microservice systems. We have made this source code publicly available. Thank you for your attention, and I look forward to your questions and discussions.